Welcome back. So this is 2.7 implicit differentiation. This is going to tell us how we can take derivatives of equations that are not in function format and what we do with these right here. So the idea is you're taking the derivative of a function with respect to x. That's typically what most of our derivatives are going to be based on. This will be with respect to other variables as well at other points. We'll get into that kind of stuff. We get into unit 4 and 5, talking about derivatives with respect to t and then r and other things. But if there's a variable that's not x, we need to include that d blank dx term next to each derivative. Perfect example. If I want to take the derivative of y cubed with respect to x, not with respect to y, just respect to x, it's 3y squared, your basic power rule, but then the dy dx term has to come after it. Okay? If I had like a z to the fourth, and I want to take derivative with respect to x, that'd be 4z cubed dz dx. Okay? And then since most of our problems, if you recognize that dy dx is one way to write our f prime of x, so in these kind of situations where it's only y and x's, you're going to have to then rearrange the equation and get dy dx all by itself. All right, so there's a couple different scenarios that this will occur with. So we're talking about using implicit right here to solve for dy dx. So we take each of those derivatives. Negative 3x cubed is a negative 9x squared. 5 is 0. 5x is 5. And then 5y squared, we use our power rule, we get 10y, but because we took a derivative of a y there, we need that dy dx term right afterwards. So now we need to solve for dy dx, so we subtract the 5 over. And then I don't want the 10y, so we divide it over. So our dy dx term is negative 9x squared minus 5 over 10y. Now, it is a fraction, so if we could simplify, we would need to. So if that 9 had been, let's say, a 15 instead, everything can divide by 5 there in the top and the bottom, so we'd have to do that. If there were negatives everywhere, we should reduce the negative. Whatever your basic fraction rules still are, those would still apply each and every time for this stuff. So that's your basic implicit. So it doesn't have to be just simply a single y term. We could have multiple y terms. Each time we take a derivative of y, though, even if the y disappears, like here the negative 5y is just negative 5, we still have to have that dy dx term. So again, 2 disappears, 4x squared becomes 8x, 3y squared becomes 6y, and then it's dy dx. So then from here, since we have dy dx terms, there's 2 of them, we need to combine them as best we can. Now, we'll subtract over the 6y. Typically, though, they're not going to be the same kind of coefficient, so I can't actually combine them into a single dy dx term. Like if they were both 6 dy, like if I had a 6 dy dx and a negative 5 dy dx, that adds to be a positive 1 dy dx. That's perfectly fine. Your basic algebra rules apply. But negative 5 and negative 6y can't combine, but I can factor the common dy dx term out. And here's the thing, you're trying to solve for dy dx, so even if they had further in common, let's say instead of being a negative 6y, that was a negative 10y, I could take a negative 5, not trying to. The goal is to get dy dx completely by itself, so if they have anything further in common, I'm not taking anything further out, just only the dy dx term. We divide over, we get 8x over negative 5 minus 6y is our answer for dy dx. I also want to point out, if they had asked us questions about, like, let's say they want us to write a tangent line at the point, let's just say, okay, I have no idea if this number works. Let's just say it's at 1, 2. I have no idea if that's the actual that would work if I plug in 1 for x and 2 for y. I'd have to adjust some stuff there to make it truly work. I'm just kind of making up on the spot right now, so let's not worry about that. So tangent line, we need to identify slope. Dy dx is slope. So dy dx would be 8 times 1 over negative 5 minus 6 times 2. We get 8 over negative 17. So it'd be y minus 2, 8 over negative 17, x minus 1. Okay, so again, keep in mind, if they ever talk about tangent lines, but you had to do implicit differentiation, it's still the same thing. You're plugging into dy dx, your quarter points, and then that's telling you the slope of your tangent line. Now, when they do these things correctly, they'll have everything matching up so the numbers do match up in there. which this currently does, and I would have to just change the +2 to whatever number I would need to make the full thing match. Not really worrying about that right now. All right, now, you'll notice here, there's only one y term in the problem, but it's part of a product. So this is going to require a product rule situation going on right there between the 3x squared and the y cubed. So our derivative 2 becomes 0, x cubed becomes 3x squared. We now have a product rule. So product rule tells us derivative of the first function, which would be 6x. We leave the second function alone. And because I did not take a derivative of y, I do not write a dy dx there. The y cubed is left alone. I'm not including dy dx. Now, plus 3x squared times 3y squared, that now gets a dy dx term because I took a derivative of y. And then 4x squared becomes 8x. So I'm going to go ahead and move everything over to the left side. Negative 3x squared minus 6xy cubed minus 8x. And then I'm going to have a 9x squared y squared in front of my dy dx, which I then divide over. So dy dx would be negative 3x squared minus 6xy cubed minus 8x over 9x squared y squared. Now, in this case, you'll notice every single term in the numerator and denominator has an x. They almost have numbers divisible by 3 because of the 3, 6, and 9, but the 8 doesn't work. But there's an x everywhere else. So I can divide everything by x and get negative 3x minus 6y cubed minus 8 all over 9x y squared. So always be on the lookout for, can I simplify this rational function? Can I simplify my fraction any further? Because if you can, you do need to. Whether it's a number or variable, you need to always simplify. So product rule is a common thing they'll include for these implicit differentiation questions, so watch out and be very careful. You only put the dy dx term after we have the take derivative of y. We do not include it as part of when we left the y alone. So that's why it was just 6x derivative of 3x squared, and then the y cubed was left alone. There was no dy dx term. All right, so final one. So we have a y cubed that's by itself. We also have a product rule going on here. So we're going to have two dy dx terms showing up. We're going to get negative 6y squared dy dx. The 3 goes away. 3x squared becomes 6x. This is, again, a product rule. Derivative of 2x cubed is 6x squared. Y is left alone. Therefore, there is no dy dx term. But we take the derivative of y, we get a 1, and then dy dx, because that is our derivative of y was taken, so we need to include dy dx. We're going to go ahead and subtract it over to the other side. So we have negative 6y squared dy dx minus 2x cubed dy dx equals 6x plus 6x squared y. We can factor only the dy dx out. Yeah, they both have negatives. Yeah, they both can divide by a 2. Don't want to do that. I only want to get dy dx by itself. So I don't want anything else factored out with it. So we divide all that over. We get the 6x plus 6x squared y up top. Negative 6y squared minus 2x cubed on the bottom. So this one does not have an x in common everywhere because while there's an x in 3 spots, it's not there for the negative 6y squared, so I can't divide by x's, but 6, 6, negative 6, and negative 2 can all divide by 2. So this would become a 3x plus 3x squared y over negative 3y squared minus x cubed. That's our dy dx value. And again, as I did in the couple examples ago, if they ask us what is the value of the derivative at this point here and they give us an x and y value to plug in, we just plug it in. That will give us our slope for the tangent line, which then we could also do a negative reciprocal to get a normal slope to do our perpendicular there, whatever we need to work with. All right, so that's our implicit differentiation. So our last video involving the polynomials will be the multiple derivatives, talking about finding second, third, and so on derivatives. And then from there, we'll get into the non-polynomials. So we'll re-explore this implicit in the context of a non-polynomial, having like, sine of y. What does that do? E's, ln's, all that kind of stuff. So I'll see you next time for those videos.